Its course can be altered at will while in flight. We have progressed since our early 1916 efforts, but there is still much work to be done, much improvement to be made toward the goal of the effective guided missile. As a result of past experience implemented by constant research, this goal is rapidly being approached.
It was an accumulation of technologies looking for a home. We had a bunch of things come out of the technology-based program: a thrust vector control rocket motor, new warhead concept, new fuse concept, 6 new guidance control concepts. Put those technologies together to form an air-to-air missile. We looked at the shortcomings of the present systems and said, we're going to solve all of those shortcomings.
And now, way off Boresight. The story of guided missiles is the story of farther and faster, more accurate, more deadly, more technology applied to guidance and warheads and fuses and avionics and rocket motors. It's a story, too, of hits and misses. Air-to-air missiles particularly present tricky technological challenges. Size limitations make for limitations on range and warhead load and guidance and control flexibility. China Lake's early establishment of a technology program that encompassed nearly every aspect of rocket and guided missile and fire control development, combined with Sidewinder's unprecedented early success, resulted in proposed next-generation air-to-air missiles for 3 very different generations. This isn't simply a story of super Sidewinders, though, but of the unique advantage of China Lake. The unique advantage of being able to develop an entire missile from ogive to nozzle in a single place. Some of the most potentially potent accumulations of technologies are little known these days, at least by name. Some, like the HAP, get hidden by heavy curtains of classification, and no one hears a great deal about those that just didn't make it. Some of China Lake's programmatic misses represent, nonetheless, tremendous technological achievements. Diamondback, AGILE, and the ACIMD stand out as representative of those technological achievements and of their respective generations. China Lake's responses to the threat as it evolved from waves of nuke-laden bombers through new generations of super-capable fighters to long-range supersonic heavies equipped with sea-skimming ship killers were as varied and as edgy as the technologies leaving the laboratories. Working with the fleet to solve the shortcomings of its current weapons and to provide the technology to help meet its future needs, China Lake would apply its engineering experience to its tech-based audacity to combine highly advanced sensors and seekers, cutting-edge warheads, and new integration and avionics schemes, with the pinnacle of the propulsion technology of the period. And since you could see it, it was always the motor that stood out. Diamondback's huge demand-thrust liquid fuel engine, AGILE's wingless, finless, radically maneuverable thrust vector scheme, ACIMD's distinctive deep-throated rocket ramjet. In the late 1950s, China Lake began the development of Diamondback, the putative super sidewinder of its atomic-centric generation. Diamondback would feature an advanced sidewinder seeker with greater range, accuracy, and stability, mated to a larger airframe, one that, against the conventional wisdom, maintained the winder's well-proven canard control, but was powered by a high-tech variable thrust liquid propellant motor that provided both high speed and long range. Like its contemporaries, Diamondback would have the option of a nuclear warhead, the only potential part of the missile that China Lake had no part in. Coming out of the hot and Cold War 1960s and drawing on its quick-turn propulsion technology project, AGILE was China Lake's attempt to get a sidewinder way off Boresight. The iconic AGILE was the multi-mode guided, purely thrust vector controlled version, although there were both light and heavy versions in development. And there was a competing Aero AGILE version with advanced guidance and energetics, but more conventional canard control. AGILE also included the helmet-mounted sight concept that would get so much press in later years. The early 80s saw ACIMD, China Lake's nameless entry in the race for a fast, long-range weapon to protect the fleet from the new generation of anti-ship missiles before they were launched. ACIMD combined multi-mode guidance, a smart warhead, and an integral rocket ramjet into a cutting-edge Sparrow-sized airframe to replace the at best marginal Phoenix in the outer air battle role. None of these survived of itself. All three were victims of budget at some level, and of politics and rivalry at others. The quest for commonality was a factor in the demise of all three, as were issues of cost and complexity. The failure to freeze a final configuration helped doom AGILE, and the assumed end of the Cold War helped to bury the ACIMD. However, Sidewinder's proposed big brother fed a new generation of short-range snakes, and some interesting experiments supporting space exploration. AGILE's perhaps too edgy technology saw some amazing application. And would help provide the basis for missile systems 2 decades or more away. The helmet-coupled sight concept remained in the works too, waiting for technology to catch up. It's too soon to tell just where the advancements of ACIMD may lead, at least in public. In the end, it always seems to be the Sidewinder that survives, the multi-decade mainstay of the fleet's fighter cap. From the Straits of Formosa to Bekov, Bosnia, and Basra. But that's another story.
Under development at the Naval Ordnance Test Station at China Lake is a rocket propulsion system for ordnance devices and manned space vehicles. A liquid rocket motor using hypergolic fuel with unlimited start and stop capability and infinitely variable thrust regulation from shutoff to full rated power. Basically, the system controls the flow of two storable liquids through a variable area injector and into a double regeneratively cooled combustion chamber. By means of a mechanical, electrical, or hydraulic throttle mechanism, the areas of the injector orifices may be varied over the full range from 0 to full open, with corresponding variation in propellant flow rate and thrust. The injector mechanism incorporates but a single moving part, providing utmost reliability with almost unlimited life. The Knott's variable area injector, which is the key to the system, permits full range throttling with uniformly good injection. This uniformity is essential to smooth, efficient combustion. As the throttle handle is advanced from the shutoff position, thrust is immediately developed. No separate ignition system is required as hypergolic propellants ignite spontaneously upon contact of fuel and oxidizer. Further advancing the throttle handle increases thrust, while retarding the handle reduces thrust or stops the action entirely on demand. A radio-controlled servo mechanism for throttling is currently being installed in the Knott static firing facility. And designs for a command navigational space vehicle are being studied as a possible application for this system. RARE is an experimental propulsion system intended to greatly increase the range of airborne missiles. It is a combination of two ideas, a double-base solid propellant rocket booster and a solid fuel ramjet sustainer. The study of air-breathing propulsion systems was begun in September 1955 to gather systematic design information. Solid fuel for the ramjet is a metallic composition, largely magnesium, producing a fuel-specific impulse of the order of 1,000 pounds of thrust per pound of fuel per second. The weapon, flexible in design, operates at altitudes and velocities of other small aircraft-delivered missiles. It is estimated to give 3 times the range of a similar-sized solid-fuel rocket sustainer, perhaps ranges of 10 to 150 miles and speeds of Mach 2.0 to 4.0. A 5-inch diameter rare propulsion test vehicle has been designed, built, and statically tested and is now being successfully flown. The rare test vehicle, separating from its launcher at Mach 1, is boosted to a cruise velocity of Mach 2.3 by a double-base propellant booster motor, which occupies the after portion of the same chamber with the solid fuel sustainer charge. The pressure from the burning booster unlocks the slide valve, but holds it in place, sealing the chamber at the forward end during boost. At the same time, the burning booster grain provides positive ignition to the solid ramjet fuel. When the booster motor burns out, the chamber pressure drops and the ram air pressure in the diffuser drives the slide valve rearward, opening an air passage to the ramjet sustainer grain, thereby initiating ramjet cruise operation. When the slide valve moves rearward, it activates a pair of explosive bolts, which release an expendable booster nozzle. As the experimental booster nozzle falls away, the ramjet sustainer nozzle takes over. A prototype rare weapon would not jettison a nozzle. The tests have proved that the basic rare system works. The integral booster performed as had been planned. The changeover from boost to ramjet cruise was smooth, the ramjet furnished thrust, and the flight was entirely stable. Recent static tests have shown thrusts higher than had been calculated. Enough work has been done now to define the areas needing research before a weapon using the rare propulsion system can be developed.
The targets. The shooter. Two points separated by 1,000 yards. Or hundreds of miles. The missile propulsion system spans the distance, taking the warhead to the target. There are two basic missile propulsion systems: rocket motors and air breathers. The two most common air breathers are ramjets and turbine engines. Cruise missiles, long-range air intercept missiles, and reconnaissance platforms all require ranges beyond those reasonably expected from rocket motors. Ramjet engines, an old concept reapplied, propel our long-distance cruise and intercept missiles at speeds up to Mach 3. Like rocket motors, ramjets are a simple concept using advanced technology. Following a boost phase using conventional solid propellant, the engine's velocity forces ambient air through inlets into the engine's combustion chamber. This compressed air is combined in the combustion chamber with a high-energy fuel and ignited. The gas exits and the missile moves forward. This continuous cycle works only at high velocities because the compression of incoming air must be sufficient to block exhaust from leaving the inlet ports. Early tactical ramjets were boosted to operational speed by external rocket motors. Current ramjets use an integral solid propellant rocket motor to reach ramjet ignition speed. At rocket burnout, the ramjet inlets are unplugged, the nozzle jettisoned. Fuel flow begins, and the ramjet ignites. The missile accelerates to cruise velocity and holds this speed until target impact or fuel exhaustion. New inlet designs are under development. Combustion chamber insulation is being improved. Fuel and fuel management systems are being refined, and improved hardware for rocket to ramjet transition is being tested.
What is that?
The old fuse drop test tower in Area R is one of the original Caltech RDT&E facilities. It was built in 1944 for rocket fuse safety testing. They'd put a fuse from each production lot on a dummy rocket and drop it onto a steel plate. The fuse passed if it didn't fire, and the lot was accepted. It was an interesting enough facility, by the way, to be featured in Caltech's 1945 rocket testing book, with an illustration by the famous painter and astronomer Russell W. Porter. Amazingly, the tower is little changed after 6 decades. Amazing enough that it still exists. It's been used for other sorts of impact testing and to hoist sensor targets over the years, but it's been a while since anything's been dropped off of it. It's pretty much just an antenna platform these days.
The aimable ordnance system. A new concept in warheads and fuses can direct more than double the energy of existing ordnance systems toward the target. One type of aimable warhead uses explosive strips, which are detonated by the fusing system to selectively form the warhead. This causes the warhead to concentrate the fragments and enhance their velocity in the direction of the target. This concentration of mass and velocity can increase the probability of a catastrophic kill at least twofold over conventional warheads. The fuse detects the target relative to the missile roll plane. The target appears in one of the fuse's sensing zones. Then the target location can be resolved to plus or minus 20 degrees in the roll plane. To optimize kill effect, the fuse initiates the proper forming charges, concentrating the warhead blast and fragmentation. The aimable ordnance system is currently in exploratory development. Extensive testing of the aimable ordnance system is underway at NWC's Encounter Simulation Laboratory to duplicate endgame encounters. This provides data to enhance warhead aiming and burst control. In a recent warhead test, a 7-inch, 38-pound selectively aimable warhead catastrophically damaged a J-57 engine. The 25-foot standoff was more than double the kill radius of conventional, non-aimable warheads. Testing showed the aimable ordnance system has a greater effective kill radius than existing ordnance systems of equivalent size and weight. Lightweight warheads could be developed with the same effectiveness as current non-aimable warheads. The aimable ordnance system is ideally suited for countering threats ranging from small, fast anti-ship missiles to large standoff jammer aircraft to selected surface targets. The aimable ordnance system would improve effectiveness of most anti-air missiles. The system should be available for advanced development in fiscal year 1980.
Question: what's the best dogfight weapon for today's high-performance aircraft?
That's easy. It's a machine gun. I did pretty good with my Lewis.
But you wouldn't now. The enemy is too fast and maneuverable. Boresight time is low. Firing opportunities are minimal.
Well, so I guess that makes the best dogfight weapon a missile, right?
Right.
Well, you Navy guys must be pretty well fixed with Sparrow and Sidewinder.
Not really. They're good missiles, but they were designed as interceptor weapons for standoff delivery against large, non-maneuvering targets like bombers, not for close-range engagements with small, highly maneuverable aircraft. You see, Navy planes are carrier-based. We need range for attack escort, and we need mission flexibility. Our aircraft are loaded with avionics, ECM, communications, and navigation gear. All these add to the wing loading, so we must sacrifice a certain amount of maneuverability. The enemy, on the other hand, is strictly a point defense fighter operating close to home. His aircraft was designed to do just one job, well. We haven't had much luck engaging him with our missiles. In Southeast Asia, considering all air-to-air weapons, it's been taking an average of about 10 missiles to down one fighter. The best weapon has been Sidewinder, but they've still been needing about 4 firings to get a kill. In about 25% of the hassles, we can't even move into launch position. But once we do, only about 1/3 of the time do we get a kill. There's just too many rules of thumb for firing these birds. More rules than pilots have thumbs.
But you still need long-range missiles, don't you?
Of course. Sparrow and Phoenix will stay in the arsenal, but we need an improved dogfight weapon.
Well, can't the missile be modified for close range?
Yes, and it is, but only for an interim capability. You see, there's one basic problem that must be considered. In your day, you aimed the weapon independent of the aircraft. We can't. Before launch, the weapon is fixed. We have to aim the aircraft and hold it close to target. That's hard to do when your opponent is twisting through space near the speed of sound.
Sounds like a pretty big gap between my guns and your missiles.
You better believe it.
You know, you guys have sure made things complicated. Now, in my day, it was pretty much one man pitting his skill against another. The airplane was almost incidental.
In that respect, it's still the same. Man against man. In fact, we refer to a weapon system. Missile, aircraft, man. All part of a chain, only strong as its weakest link.
And it seems the weakest link is the weapon.
That's right.
Hey, you ever thought about going back to a Lewis gun? Mounted on a Sopwith Camel?
Let's go even farther than that. Let's look at the basic link in our weapon system. If he has to defend himself, what's the simplest weapon we can give him?
What about this?
Excellent. Now notice, wherever his body turns, the gun is pointing.
But what about that missing link in your weapon system? What happens when your man's strapped to an aircraft with his hands full of controls? What are you going to do, stick the gun on top of his helmet?
Not quite.
Okay, so you put a little missile up there, synchronized to shoot through the propeller, right?
No, but you're getting closer to the idea. Suppose we slaved the exterior missile with the pilot's head.
You start rotating that missile during fast maneuvers and you got yourself a nice set of speed brakes.
We wouldn't have to turn the missile, just the seeker head. That way, whatever the pilot sees, he can hit.
Yeah, but things have changed a lot since I was flying. I never pulled more than about 2 Gs in my life. Damn near killed me. Now, what about when your guys are pulling a 7G turn and some MiG streaks by? Now, how's he going to move his head fast enough to aim a missile?
You'd be surprised what today's pilots can do during high-G maneuvers. China Lake and VX-4 staged a series of hassles between pairs of F-4s. We had instrumentation cameras on the pilot and RO throughout the flights. We tracked the planes with radar and looked at their instrument panels so we could tell the G-forces on them. We learned that the men could move their heads to track their targets under any acceleration encountered during these hassles, and that was up to 8½ Gs. We also learned that during the critical first 90 seconds of most engagements, no weapon carried by the F-4 could have been launched.
Okay, I'll buy the pilot's capability. But how are you going to get your missile to hit your target if it's streaking by in the opposite direction?
First, there were studies. Enough to warrant the Naval Air Systems Command sponsoring an advanced development at the Naval Weapons Center, China Lake.
Enough with the commercial. Let's get to the story.
It starts in the cockpit with the need for a visual target acquisition system called VTAS to allow full heads-up operation. Through a fiber optics bundle in the helmet, a reticle is holographically projected at infinity. The pilot moves his head to align the sight with his target. Tiny light sources embedded in the helmet project light onto lateral photodetectors mounted in the cockpit. The system knows by the position of the light falling on each detector where the pilot's looking.
What about direct sunlight? Or hot spots in the canopy? Now, won't they louse up the reading?
No, not at all. The light sources are infrared and coded. No way to confuse it with any other type of light.
Well, wouldn't radar be just as good for finding your target?
No. Out of 721 enemy encounters in Southeast Asia, only 26 were first detected by radar. The rest were all initially sighted visually. Current radar is limited to a forward plus or minus 60-degree field of view. With VTAS, the field of view is that of the pilot's. There are no restrictions to his position. He can be anywhere in the cockpit. He can even have his head rolled up to 10 degrees with no significant error.
What if he's way over like this? Can the system account for it?
It could, but during a high G pull-up, he'd probably break his head off.
Well, now, come on, you're going to need some 20-ton computer sitting out on the wing somewhere just to figure all this stuff out.
Not at all. The logic is comparatively simple. Aiming position data can be a direct output of the detectors.
Big, heavy batteries.
No, the system plugs into the aircraft's AC supply.
What about all that extra weight in the pilot's helmet?
5 ounces?
Okay, now, how does the pilot know that the missile is actually seeing what he is?
Missile status lights are displayed with the reticle to tell the pilot when the weapon is locked on and ready. If there's no lock-on indication and the pilot has his target in sight, all he has to do is roll his head slightly. He continually flies with his head out of the cockpit. Anywhere he turns, the missile can look.
How can you do this without moving the missile?
We've developed several new 3-axis seeker platforms capable of a 270-degree total field of view. This matches just about anything the pilot can do. The platforms will have a slewing rate of 200 degrees per second, which exceeds the seeker's tracking rate of 120 degrees per second.
What's the difference between tracking and slewing?
Slewing means the pilot and missile are looking for target. Tracking means they found it and are following it.
Okay, you got the pilot and the missile looking at the target. Now what happens?
Once the missile sees the target, it must be able to track it on its own without the pilot's help. Ideally, it should track it in all aspects, tail, nose, or beam. We can either use a seeker that senses infrared radiation or one that tracks it in the visual spectrum. 2 IR systems are being investigated. Both use multi-element detector arrays for increased sensitivity to provide nose-on tracking. One uses a cruciform arrangement of 8 tracking elements and 4 countermeasure elements. Infrared radiation is focused on the elements through a set of lenses. This seeker has already been tested against non-afterburner targets and has been effective head-on at ranges up to 5 nautical miles.
What happens if the enemy drops a flare? No, won't the missile be decoyed?
No. Both IR seekers are being designed with logic that provides flare rejection.
What's the other IR system like?
This one has a linear array and uses a mirror instead of lenses. The reflective and refractive systems have advantages and drawbacks. We're evaluating both seekers to arrive at an optimum design.
You mentioned another type of system, something like TV.
Yes, that's the electro-optical system being designed by the Naval Weapons Center. A Vidicon tube replaces the IR elements. The seeker uses area balance processing and tracks for the center of apparent mass. The system is background adaptive, so it won't be decoyed by clouds, ground, or mountains.
How can it work at night?
Who hassles at night?
Okay. You've got your missile looking at the target and locked on. But how are you going to get it to do a quick 180?
By a reaction steering device similar to that developed for the Wagtail program. The missile is steered by a gimbaled nozzle powered by actuators buried within a gimbal ring. The nozzle can vector 20 degrees in any direction within 25 milliseconds. This means the entire missile can make large angle turns rapidly. Maneuvering forces are instantly available, regardless of launch altitude or speed.
Looks like you got it made.
Almost. We've got the missile to target. Now we've got to be sure to get the kill. We've designed an active optical target detector. The TD will give us size discrimination, closing velocity compensation, edge detection, and sharp range cutoff.
Why do you need all that?
We'd like to have the missile detonate near the target's center of mass, regardless of the intercept geometry. That way, we're sure of doing the maximum amount of damage. The TD exhibits a high degree of immunity to electronic countermeasures, and if the missile should actually strike the target's airframe, we have contact backup.
I guess that baby must pack a pretty heavy warhead.
No, only about 30 pounds, of which approximately 14 are high explosive. The proportion of charge to metal provides high fragment energies. Arming a detonation is from a unique safe-arm device. The effect of the primary fragments is like a blackjack. The target is literally slugged to pieces.
Looks like you're closing that gap with a bang.
We think so. We'll be capable of matching the pilot's ability in most areas. With seeker gimbal limits of plus and minus 135 degrees and a slew rate of 200 degrees per second, our new missile will provide rapid heads-up lock-on and launch against targets in all aspects at ranges from 1,000 feet to 5 nautical miles. The missile's extreme maneuverability for off-axis firing, along with its improved fuse and warhead, will yield a quick, catastrophic kill. In all, a system providing increased launch opportunities, fast reaction, and improved lethality.
Fantastic. You got a name for this super missile?
We're calling it AGILE.
AGILE. Sounds appropriate. Hey, let me ask you something. Now, is all this just a lot of theory, or do you actually have some hardware to show off?
Both. One of our preliminary studies involved digital simulations of air combat maneuvers. All known performance parameters of friendly and threat aircraft were programmed into the computer for a series of electronic dogfights. The LTV simulator was the next step towards real life, allowing the addition of the pilot to the loop to provide more realistic dogfight simulations. It also allowed us to do some things we couldn't do at Air Tevron 4, fly combat against enemy aircraft. We could also simulate U.S. aircraft currently on the drawing boards. The studies prove that the effectiveness of every one of our fighter aircraft could be greatly enhanced by carrying an off-Boresight, all-aspect weapon. We also learned that with such a weapon, attack aircraft such as the A-4 and A-7 could have a significant self-defense capability. Next, employing results from previous simulations, we began a rather unique computer operation. The goal was to optimize a missile design by flight simulation of various configurations. We were able to study the various trajectories produced by different launch conditions. The simulations were conducted at 100 times real time to generate complete missile envelopes rapidly. Now we had our weapon parameters, and we began development of the components of the missile that would do the job. One of the key pieces of hardware, the VTAS, has been successfully flight tested. The holographic sight on an early phase VTAS has had 14 range flights and was shown to be completely free from the effects of buffet or G loading. During 1970, the two early phase IR seekers were tested against various types of airborne targets at Point Mugu. Both demonstrated tracking capabilities up to 5 nautical miles against non-afterburner targets. The center's EO seeker and 3-axis platform have demonstrated large gimbal angle and tracking rate capability. In June 1970, this system was subjected to 2 sled launches at NWC. It survived and functioned well under this environment. During 1971, an electromechanical safe arm device was formulated. 2 breadboard models were built to test and evaluate the components. Starting in 1970, several series of warhead firings have been conducted to investigate the design parameters. The product was this baseline configuration. Design iterations are continuing. The thrust vector control system has been subjected to bench testing and firing trials. Performance is excellent. First firing of a solid propellant all-boost motor was accomplished in July 1970. The rocket motor was subjected to high acceleration tests to determine G sensitivity. There was no change in the burning rate. The use of thrust vector control allows a clean airframe not requiring large aerodynamic surfaces. This means more missiles can be carried and aircraft installation is simplified. The airframe is a product of wind tunnel evaluation at NSRDC, AEDC, and private contractor facilities. The result is this clean-bodied design, 93 inches long, 8 inches in diameter, and tapering to a 5-inch nose. Stabilizing tail fins are free to rotate to remove the effects of aerodynamically induced roll. Although the baseline design is to be rail-launched, it does have the potential for tube launching if desired. The success of the airframe design was demonstrated in July 1970 with this ballistic launch. In September 1970, a second ballistic test vehicle was successfully air-launched from an altitude of 10,000 feet at a speed of 0.8 Mach. The third ballistic test vehicle was fired in August 1971 to evaluate flight test vehicle subsystems. All significant test objectives were met. The launch of the first flight test vehicle with an actuated thrust vector control nozzle occurred in February 1972. The vehicle, which carried an onboard flight programmer but no seeker, successfully performed a large angle turn. The firing verified the concept of a clean airframe maneuvered by thrust vector control. The second flight test vehicle was successfully launched in April 1972 to investigate the induced yaw and overturning moment phenomenon. The vehicle dramatically demonstrated the missile's quick turning ability. A third flight test vehicle was launched in June 1972, the most grueling test to date of the thrust vector control system. Now, at the start of the first turn, the missile reached a velocity of 1,525 feet per second. The turn then continued to an angle of attack of 110 degrees. Despite angular accelerations up to 4,000 degrees per second squared, roll rate and yaw remained under good control. Evaluations not only showed no unfavorable flight characteristics, but proved the AGILE airframe to be more stable than predicted. The missile's capability is more dramatically demonstrated by this replay of the launch, seen in real time.
Well, that's just great. Hope you have as much luck with AGILE as I did with my Lewis.
Thank you.
Well, keep 'em flying.
That's our job.
In this feasibility demonstration, a 0 to 1,100 pound variable thrust rocket motor raised the vehicle smoothly to a height of 60 feet. Was lowered and hovered at 30 feet, finally softly landing at a touchdown velocity of 5 feet per second. This test demonstrated that a vertically descending craft can precisely be controlled by a variable thrust engine. On the second and third flights, tests were made on an optical sensing device for automatically controlling the variable thrust motor in open loop operation. This test was to determine the effects of engine vibration on the operation of the device. A pilot controlled the variable thrust motor, and signals from the optical sensing device were monitored. A third test was made on 23 June 1961, a repeat open-loop test on the optical sensing device to determine if a minor pulse generator problem had been resolved, and to obtain the extent of vibration of the new 0 to 1,300 pound thrust engine. The vehicle ascended to 135 feet. Then the thrust was terminated by the pilot, and the vehicle allowed to free fall for 1.7 seconds. The pilot then applied full thrust and terminated the fall at 75 feet. The monitored signal indicated that the scanner operated successfully and that the engine vibration was of low intensity.
The vertical seeking system automatically steers the seat upward, regardless of the aircraft attitude at the time of ejection. A pilot can safely eject from an inverted aircraft 50 feet above the ground or at deck level from an aircraft in a 90-degree roll. The propulsion steering system uses an 8-inch spherical rocket motor in a 2-axis gimbal under the seat. Motor positioning is hydraulically controlled. The A6 cockpit was suspended 100 feet above ground level in a 135-degree roll attitude. After dropping less than 30 feet, the seat steered for vertical. The dummy-in seat separated 213 feet above ground level, and the parachute deployed normally. These tests have successfully demonstrated the feasibility of using the Mars vertical sensor on the vertical seeking escape system.